Yeah, here. So IP has 20 byte header and TCP has 20 byte header, okay? Except that IP is supposed to be, the header length is supposed to be variable because of the options. Because as we said, we never actually use that field anymore. Bismillah ar-Rahman ar-Rahim. So last time we started to talk about the router architecture, including the switch fabric and the control system, and we looked at the different types of switch fabric and how they work. We also talked about the frame structure for IPv4. We talked about many of these fields and the function for each one, and the thought process that any protocol designer would go through in order to design the protocol frame structure. We also mentioned some, let's say, pitfalls in the frame structure, some of the fields that have almost never been used, and these are some of the lessons learned based on which the IPv6 was designed, which we will talk about today. One of the very key function that's performed as part of IPv4 is the fragmentation and reassembly. And we said that fragmentation is needed when the router is connected with multiple types of LAN structure or LAN technology. For example, if it's Ethernet, each LAN technology is characterized by what we call a maximum transmission unit. This maximum transmission unit limits the maximum size of the frame that should be transmitted over any of these links. Okay? As a result, the router needs to perform, in some cases, fragmentation and or reassembly. The rules for this is that we said that if the router has to perform the fragmentation, okay, it cannot perform reassembly in the core network. And this is very important. And we talked about the reason for this is that each of these fragments, it becomes an independent IP packet that should be routed independently, and there is a possibility that some of these fragments, they will take different routes. Based on that, we cannot actually, at any router in the core network, wait for all these fragments to come because they may never come, right? So when do they have to come? In the final destination. So we can perform multiple levels of fragmentation, but we can only do the reassembly at the destination. That's very important. So if we go through a link with maximum transmission unit of 500, then the 1500 will have to be divided into 3 packets. If later we pass through another link 200, then each 500 fragment will have to be refragmented again into 200 fragments, and so on. We can perform multiple levels of fragments. So last time, we will go through a specific example with numbers. So that example is very important, and it shows you how to perform this fragmentation process. طبعا we have four very important fields that we talked about in the frame structure last time. So we have currently a packet, an IP packet of length 4,000. Okay, so we need to send this packet over a link with maximum transmission unit of 1500. So as we can tell, I mean, we need to fragment this into 3 fragments. So that's easy, right? But what will be the length, the ID, the flag, the fragmentation flag, and the fragmentation offset? So for each of these fragments, we have to specify the new length, okay, the ID, the identification number, the flag, and the offset. One thing we have to keep in mind here is that This 4,000 bytes is the length. As we said before, the length gives you the total length of the header plus the data. Okay? For fragmentation, it's important to actually work on the data and not the header. So we need to, first thing we need to do here is to separate the header from the data. Okay? So if we have a length of 4,000, this means the length of the data is 3980, right? صح كده؟ Yeah. No, 32A. لا. This is bytes. The length of the header for IP, as we said before, it's actually 20 bytes. Oh, no, we talked. So in all cases, almost all cases, the header length is 20 bytes. And that's, we can consider it fixed. Okay? So this means that the data is actually 3,980. Okay? So again, this will have to be divided into three fragments. And the first fragment will have to be 1,500, which means that the data part of this will be about minus 20, which will be 1,480. And this one, 1,480. Okay? If you sum these two and then subtract it from here, you get this, which is supposed to be 120. Okay? So if you get this summation plus this, it will be this. Voila? So this is the first thing. Type. So in terms of planning, it looks like we have to fragment to three fragments. Okay? What will be the length of the first one? 500. What will be the length of the second one? 1,500. And what will be the length of the third one? Huh? 1040. واضح كده؟ حد مش عارف دي جت ازاي؟ عارفه جت ازاي؟ Okay. So this will have to be divided into 1,480 plus 1,480 plus 1020. صح? Okay. If you get the summation of these, it will be this. Okay. طيب يبقى في الحالة دي I will have to create the first fragment by adding 20 bytes of header to this. So it will be 1,500. 20 bytes header for this, it will be 1,500. The last one will be the remaining part. When we say the maximum transmission unit is 1,500, that doesn't mean that every segment has to have 1,500. ماشي؟ ممكن the segment, or sorry, the fragment could be less than 1,500. But this is the maximum transmission unit. واضح كده؟ Okay, so this is the length of these three fields. The identification is easy. So if the identification in the main packet is X, so then all the three of them will have X. As we said before, identification here is different from the sequence number. It's not like we give different sequence or different identification for each fragment or each packet. No, this is the identification here is used for reassembly, actually, for fragmentation and reassembly. So we should mark the fact that all these three fragments, they belong to the same IP packet. So that's why we have to put the identification on all the fragments that belong to the same packet, so that when we reach to the final destination, we say that, okay, let me get all the fragments that have the same ID and group all of them into one big IP packet. واضح كده؟ طيب, so the identification is easy. Okay? The flag is also easy. What happens is that the first fragment, okay, we put the flag as 1. This indicates that that's not the end fragment. Okay? This is not the end fragment. There are some upcoming fragments later on. Okay? So here it's 1 and here it's 0. This means that this is the last fragment. So once the router at the very end or the final destination finds the value of the flag as 0, then this is a trigger for the destination or the final router to start performing the reassembly. Performing the reassembly means that, okay, so I will then prepare one packet, and then I will start fitting these into that bucket. Okay. So let me see how many fragments did I get so far, and we start putting them in the bucket. Okay. But there is another problem now. So when I start to put these fragments in the bucket, what is the sequence? Right? What is the sequence? So should I fit this here or here or here? Where? Okay? Which one goes first? Which one goes second? Which one goes third? Okay? And that comes the function of the offset. Okay? So the offset field tells me where the location of this fragment is in the original packet. Okay? So obviously the first one will start from 0. Okay? The second one, let's see. The second one is supposed to start at what?
The beginning of the other.
The beginning of the next. اللي هي كام يعني؟
1480.
1480. برافو عليك. صح. حد مش عارف دي جت ازاي؟ So the offset for the second one will be المفروض يبقى 1480. صح؟ وبعدين اللي بعدها تبقى كام؟
Plus 1480.
Plus 1480. This plus 1480. Okay? So this will tell me how to put it. However, this offset field, let's see, the offset field has, the offset field here, by the way, gives you the length of the 8-byte word. Okay? So that's a way for us to kind of compress the length of the offset, of the fragmentation offset. Okay? So each one in the fragmentation offset refers to one 8-byte word. So if we have 1480, we divide that by 8, we get 185. So the offset refers to the length of the 8-byte word. ماشي؟ واضح كده؟ So we divide 1480 by 8. We get 185, we put it in the offset. So the second one will be this times 2, صح? Which is 370. Okay? So the first one is 0, second one is 185, the third one is 370. So that's a complete answer. This way we have all the 4 fields for all the fragments. This creates 3 independent fragments that from now on they can be routed differently. We have best effort for all these fragments. One fragment might get lost, one fragment might loop in the network. They arrive on time, they don't arrive on time, that's fine. Okay? Someone might say that, okay, so if 110 here might indicate that they should arrive in order. No, there is no guarantee that they should arrive in order. But once we see 0, then the router or the destination at the end will start the process, okay? But it may actually wait for all the fragments to come. When we start the process, we start to fit the fragments in the original IP packet based on the offset. So if one of these fragments did not arrive yet, the destination may wait for a timeout and then it decides that, okay, so this fragment was lost. Okay, what do I do if one fragment from the packet is lost?
Do we decide it's all corrupted?
بالظبط. We have to. We don't have any other option. Yeah, we don't have any other option. The whole packet is corrupted. Because the checksum will fail. The packet is corrupted, which means the entire packet is lost. خلاص. We drop it. ماشي؟
Is this where acknowledgement comes in play?
لا ما فيش acknowledgement في النتورك لاير.
لا أقصد بالother layers.
في TCP هو IP will drop. خلاص IP at the destination will drop the packet.
صح
okay? Which means that in TCP you will not receive the acknowledgement. صح?
صح
In TCP, that's in TCP,
صح.
okay? TCP, the source did not receive the acknowledgement, it will retransmit, which means that the packet will go again in the network and will do all this process again.
Yeah, which means just like what we said, that we are pushing this to
To the edge, بالضبط, برافو عليك, yes. We are pushing this complexity to the edge. So the core remains a simple so that it becomes scalable. تمام كده? So that's the end of that topic. So now we need to talk about ICMP. Or sorry, the subnet mask. The subnets طبعا يعني people who have studied network one, I assume that you are masters of this topic. So you should actually يعني one of you should come here and explain this to others. Because this topic in particular يعني we spent تقريبا يعني 40% of network one studying this topic only. Okay? So you should be masters in this topic. You should try to help me. تمام? So the subnetting is all about when we have the IP address space. The IP address space, we need to divide it so that we can assign one IP to a particular host. At the end of the day, one host takes one IP. مفروض. Or could be more, but يعني the standard is that one host should get one IP. Then, so this IP, usually it will be in a range of IPs that's assigned to this particular LAN. ماشي؟ طيب. هو philosophically بقى يعني or fundamentally يعني why do we need to do subnets أصلا? Why do we need to divide IPs into ranges and have this LAN or this part to have a range of IP address, okay, in a contiguous way, or it should be like in a way continuous. Okay.
So I can populate my routing table.
برافو عليك. So that's a good way of thinking. صح؟ مظبوط. So if I can divide the range of IP addresses in a contiguous way, this will allow me to refer to this entire network using one routing entry that refers to this network. صح؟ Then, what is the advantage that this will give me if I perform routing? Why do we have to do أصلا يعني routing? Why not in connect all of them using one switch خلاص? Why do we have routers أصلا?
Scaling issues. Scaling to so many.
يعني even in QU network we have tons of routers. صح? So why not have the entire QU network connected to one switch, connects all the everything خلاص.
Distance.
The routers connect you to like an external internet, switches only.
هو صح, routers will connect you to one router still at QU, one router which is the default gateway connects the QU network into the internet.
Scaling, we
But
never
still.
know how many hosts we want to send.
نعم.
We never know how many hosts we are sending. We plan for like maximum, which will never like happen. Really.
So you mean like
Scaling, like this one, I can like scale this for like million users, for example, but I cannot.
in the network. يعني in a way that's partially correct. صح, مظبوط.
Can switches assign IP addresses or no to devices?
Yeah, switches do not assign. بس احنا that's fine. I can connect all the hosts to physically. So you can connect all the hosts physically to one switch. خلاص. Why do we need to put routers in between? يعني what advantage does routers introduce in the network?
The location.
Logic هو اسمه logical separation. Logical separation. So when you have a network like this, okay, in one LAN for us is one broadcast domain. Which means that any of these hosts will send anything, okay, everybody can listen. صح؟ تمام كده؟ So imagine if we do this on a scale of one LAN that connects مثلا millions of users. All of them, they will be connected physically, which means that all of them will form one huge broadcast domain. طبعا there is an implication in terms of security. There is an implication in terms of overhead, because 1 million users, if any of them sends anything, everybody else can listen. It's like wireless, and you're sending a wireless signal with very, very large range, and everybody can listen to it. Of course, there is a big overhead, and there is security issues as well. Okay, so that's why it's highly advisable that you should try to divide your network into logically isolated sub-networks. This allows you to control these broadcast domains, which will allow you to provide some rules. If a host from here cannot send to a host on this network, for example, I can put the rule like this. Okay, when a host here sends anything, these hosts cannot listen to it. Okay, so routers provide some logical separation. This is very, very important and very efficient in terms of network planning. We're talking about network planning issues here. Okay, so it's always advisable to put routers so that we provide this logical separations. So each interface in the router can be connected to a particular LAN, which will be represented using one broadcast domain, one big broadcast domain, right? And we could have different technologies. We could have this LAN, مثلا, can use wireless LAN. This LAN can use Ethernet. This LAN can use even satellite, whatever. ماشي? So there is logical separation. But within this LAN, all of them are physically connected to each other. Physically connected to each other. Okay, which means that anybody sending, everybody will listen. ماشي كده؟ طيب, so this is what we need to talk about. So, as you said before, one logical reason is that when we have contiguous IP addresses for these hosts, this will allow us to refer to this particular network using one entry in the routing table. That's what we need to discuss. How do we do this? How do we plan the routing table inside this router to be able to perform routing between these hosts? Okay. If we look at this network here, we see that there is something common between all of them. اللي هو ايه؟ 223.1.1 صح? This part is common between all of them. So this is the network part. And each host has a specific identification, which is 1, 2, 3, 4, and so on. This is the host part. So if I want to refer to this network, I refer to this network with the common part that groups all of them into one, which is 223.1.1.0. Okay? 0 here means don't care. This 0 in the host part means that this part could be anything. Okay? Type. So IP version 4 has, as we said before, around 4 billion addresses. صح? And you might think that this is large enough. However, of course, 4 billion nowadays is nothing. And in fact, even in the past, it was, people started to observe IP address exhaustion since the 80s. They started to have this phenomena of IP address exhaustion. Okay? So the range of IP addresses is not enough. So at that time, the standard developers, they have been divided into two separate schools. One school of thought, okay, tried to fix IP version 4 gradually. Okay? They believe the fact that IP version 4 can still survive with the address exhaustion. Okay? Another school of thought, they started to take the revolutionary approach that Okay, let's think outside the box. What do we need to do? And they started to work on IP version 6. Okay, using by all the lessons learned and stuff like that. And let's just design everything from scratch. Okay, so each school of thought has serious implications. Yeah, it has many implications to this kind of thought that they have went through. Okay, right. So here we'll start to talk about the first school of thought that they started to gradually improve IP version 4 to try to address this address exhaustion. Okay, so in the past, in order to understand what CIDR means, I have to give you a bit of a history. That in the past, we used to have what we call a classful IP addressing. Okay, again, we studied that in Network 1. Classful IP addressing, they said that, okay, so we need to, in general, yani, the IP address needs to be divided into two parts. Okay, the IP address itself, which is set in the packet, needs to be divided into two parts. One is called the network part, and the other is called the host part. Okay? So this network part is supposed to be common between all the hosts in the same subnet. So for example, so this, I have to have a way, okay, in the IP address itself to say which part is network and which part is host. So we need to have a rule, because this is what we are going to use back in the routing table. In the routing table, we are going to mainly use the network part, okay, for routing. Okay? So we need to have a rule, okay? So one logical rule could be, okay, so let's fix the network part. They didn't do that, unfortunately. Okay? Why? Because, again, discrimination comes in. So in the past, they used to have what we call a classful IP addressing. Classful IP addressing ده قال لك ايه بقى خلاص احنا ايه the first byte from the left in the IP tells me what class you're in. And based on your class, you will be categorized in this category. And that means that the network part will be like this and the host part will be like this. كمثال. If the first byte from the left is from 0 all the way to 127, okay, we will call you class A. Class A has the largest host part, which means that the network part will be, so this is the network part, and this is the host part. The network part will be 8 bits, and the host part will be 24 bits. Okay? So once we see the first number, the first byte, we see it, مثلا ايه 10 dot something. Okay, so this means that this 10 is the network, and everything else is the host. 127 dot something. So this means that 127.0.0.0, this is the network address. Okay? And everything else is the host. تمام كده؟ That's easy. If you are from the range of 128 all the way to 191, you are class B. Sorry, خلينا بس ننزل تحت شوية. العملية مش aligned قوي يعني. So from 128 all the way to 191, you will be class B. This means that the network part is actually 16 bits, and the host part is 16 bits. طبعا ده refreshment للناس بتوع network 1 طبعا. It's supposed to be يعني boring stuff. يعني احنا شرحنا الكلام ده يعني مرارا يعني. اوكي؟ تمام كده؟ طيب. So this means that these types of networks are class B. Why? As you can see, the 16 bits gives you less address space. طبعا 24 bits gives you a larger address space, which means that you can have up to a CAM host for each network. 2 to the power 24 bits. Wow, huge. Okay? And if you are from 192 all the way to 223, you are class C, and this means that the network part is 24 bits, and the host part is only 8 bits. معايا? Okay? Forget about class D and E, because obviously for each byte you have from 0 all the way to 255, right? But here we reach 223 only, صح? But we can reach up to 255. The remaining part is actually class D and E, but we don't have to talk about them because these are used for multicast. ماشي كده؟ These are the ranges, class A, B, and C. Okay? What's good about this? What's good about this is that خلاص, once I look at the first byte, I know which class you're in, and I can separate the network part from the host part, which is very important. I need this for routing. So that's an easy thing. It's easy, صح? It can be applied easily. That, in fact, led to a very, very fast IP exhaustion. It was terrible. This is a terrible design. Okay? And people, they realized how terrible it is after they started to implement that. Okay? Why? If you look at this simple approach, although it might sound like it's simple. It's a bit corrupted now. Let's just try to model the address space using a pie chart. So if I model the address space as a pie chart, okay, we can realize that if you have 24 bits for host and 8 bits for class A, okay, this means that class A in terms of address space takes how much of this pie? Half. Half the pie. Okay? Why? Because we have 128 networks, يعني 128 networks بس, all over the world, huh? Now we're talking about the entire Earth, okay? We have in the entire world only 128 networks in class A. Okay? بس. فthey used to give it بقى مثلا ساعتها بقى IBM مثلا واخدين, يعني I used to work in IBM, we used to have IP address 9 dot something. Wow, 9 dot something ده يعني ناس بقى يعني very VVIP. Microsoft بقى كده يعني. تمام? Only 128 networks all over the world. They can have this class A thing. Okay? Each one بقى could have 2 to the power 24 hosts. Huge address space. Okay? طيب, class B takes 1/4. Okay? Class C takes 1/8. And then this is class D and E, which we don't have to talk about. Okay? Can you see about what's happening here? The address planning in this case is very coarse, which means that very few networks, they have half the address space. And the class after it, okay, has, خد بالك, from, if we have 16 bits in class B, okay, we don't have to go through this, but the number of networks in class B is 2 to the power 14, not 2 to the power 16, by the way. 2 to the power 14, because part of the 2 to the power 16 is actually assigned to class A, but we have to remove class A from the equation. Okay? So we have 2 to the power 14 networks, which is larger number of networks. Each one has 2 to the power 16 hosts. Layer. Okay? And all of them collectively take only 1/4. So more networks have less number of hosts, and all of them collectively has less number of address space. And see the same thing. You have very large number of networks, okay? 2 to the power 21 networks, okay? Huge number of networks. They have 2 to the power 8 hosts only, and they consume only 1/8 of the pie. So the address planning in this case promoted huge amount of discrimination and led to extreme address exhaustion. Why? Because definitely IBM will not use, well, Microsoft, they will not use 2 to the power 24 hosts. Okay? So many of these addresses are actually wasted. Okay? But the good thing about classful is that we don't have to store in the routing table any information about how to separate the network part from the host part. We don't have to store this. We don't have to say anything. You just look at the address, and you will be able to separate the network part from the host part. Very easy. Okay? Tom, because of this classful, I shouldn't have to explain all of this, because they came up later on with another approach, and that was the first incremental improvement they introduced to IP version 4, which is the classless inter-domain routing. اللي هو CIDR. CIDR بقى introduced اللي هو ايه بقى arbitrary way of how to divide the network part from the host part. We should not discriminate and say class A and class B and class C. No, we have to store a subnet mask together with the address. The subnet mask masks the network part from the host part. If we can store a subnet mask, okay, we can use any arbitrary length for the network. It could be 8, could be 14, could be 16, could be 20, whatever. So we can store a subnet mask together with the IP address. But where? Do we store this in the packet? لا 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 لا, we don't store this in the packet. فين؟ في الrouting table, huh? Never ever hear someone says, where is the subnet mask in the packet? It doesn't get stored in the packet, huh? عشان نبقى واضحين. Okay? So CIDR بقى promotes the fact that I have to remove this بقى خلاص. So this was an introduction to just help you to appreciate how we came up with this CIDR. The motivation was the very fast IP exhaustion, okay? That happens because of the, let's say, primitive design using this classful IP address. So CIDR promotes classless. That's why they called it classless. We don't have to store the class in the, we don't have to look at the first byte and classify this address as class A or B or C. We don't have to do that. We can store the subnet mask together with the IP address in the routing table. ماشي؟ The subnet mask can be the subnet mask. The rule is the subnet mask here. If we see IP address /x, this means that x is the size of the network part. Okay. So if x, for example, is 16, this means that the first 2 bytes they refer to the network, and the second 2 bytes they refer to the host. If x here is 20, this means that the first 20 bits is actually for the network, and the last 12 bits are for the host. So we don't even have to mark the subnet mask on a byte boundary. No, we are not actually restricted to do that. Could be anything. This will give us flexibility. This will give us flexibility to try to plan and allocate the IP addresses as we see fit. if QU they need مثلا for example if QU they need 40,000 addresses خلاص I give them 64 مثلا 1000 ولا حاجه زي كده for future growth وخلاص على كده I don't have to to give them 2 to the power 24 bits تمام but I can have more granularity and flexibility in allocating the IP address واضح كده طيب ففهمنا so an example if I have this address 20.23 200.23.16.0/23 okay this means that so we have this 23 breaks this byte اللي هو third byte خليك معايا this 23 okay breaks this third byte it's very important huh? So we need to separate the host part from the network part so first we have to convert this to binary so this is the conversion of this as binary okay so 23 not 24 huh? So this means that the last byte the third byte is divided into 7 bits belong to the network and 1 bit will belong to the host. ماشي? Because we have 8 bits plus 8 bits plus 7 bits. 8 plus 8 plus 7 is 23. تمام؟ صح كده؟ So that's why this the boundary is here at 23 bits. ماشي? And if we refer to the network, this means that the host part is by default 0. By default, the host part is 0. خلاص. Okay? So for example, if we see مثلا an address that looks like this 200.23.17.4/23. What does that tell you? I can give you a number like this and tell you, okay, so give me the network address. This should be very easy. Okay? Which means that first you need to separate the host part from the network part and then convert the network part into dotted decimal notation and then this will be the answer. Okay? طبعا 23 breaks this byte so we can say that, okay, so the first 2 bytes are the same. Okay? And then this 17 بقى it has to be broken into part network and part host. So that byte needs to be converted into binary بقى. And 17 is something like this. It's actually 00010001 اللي هي 16 plus 1 صح؟ تمام كده؟ So we have to mask this at the 23rd bits, which means that this part will be zeros. So we put zeros. If we convert this to binary, it becomes a dot, 16.0. So this is the network part. This is the network address. The network address is when we mask the host part as zeros. في حد مش فاهم؟ Anyone not following? Okay. واضح كده؟ I shouldn't have this introduction really, but because some of you did not go through this before. So how does the network بقى get a subnet part of the IP? This is what we have done now. So depending on, this is the address. So if we say /20, this means that again this breaks the third byte. Okay. So this 23 breaks again the third byte and so on. So within this network, I can assign different sub-networks. Okay? So I can get one network address. So we're getting by another level. We can get one network address and redivide it into subnets. كمثال, that's what typically happens. كمثال, QU, they need to get a range of IP address. Then they get this range of IP address from Ooredoo مثلا, or from Vodafone, or maybe both. ماشي. So Orido will say, okay, so I will give you this address. I will give you an address of 200.23.16.0/20. Okay? So then QU will say, okay, so this will give me 20, which means that I have 12 bits for host. صح? So this will give me 2 to the power 12 hosts, usually -2 طبعا, as we discussed before, بس يعني in total يعني 2 to the power 12 hosts, different hosts. Okay? طيب. I as QU بقى, I can say that I will have this network as one big, huge network, one network with this address, and all of the hosts will have different host addresses. Okay? Or I can say, لا, and this design is not efficient for me. What I need to do is that I need to have routers. And as we said, the benefit for introducing routers is to provide a logical isolation between the networks. This gives us more flexibility in controlling the network more efficiently. Okay? So how do I divide this network into some logical subnets بقى? I have to do the address planning. Okay? So the address planning can be done by saying I will تفضل. لا عشان بس نكمل الحته دي وبعدين نبريك. تمام؟ فQ you might say, okay, I will take these 12 bits and borrow 3 bits, okay, as subnet, which means I have how many subnets inside QU? To the power? Huh? To the power ايه؟ 2 to the power 3. حد عنده إجابة تانية؟ 2 to the power 3 subnets inside QU. هي QU is a big network. I borrowed 3 bits, okay, which means that the address will be like this. The address now is divided into these 20 bits are given from أريد خلاص. I cannot, these are fixed. All QU host will have to have this 20 bits fixed. ماشي? And then I have 3 bits بسميهم subnet. 3 bits. Okay? And the remaining 9 bits will be host. Which means technically I divided now the network of QU into how many? 8 subnets. And each subnet will have up to 2 to the power 9 hosts. واضح كده؟ معايا؟ حد مش عارف كده جت ازاي؟ Okay? So I subdivided the big network of QU into 8 smaller subnets. Okay? Which means I have to have routers in between. Okay? The topology of these routers I can design it. مش مشكلة. بس the range of IP addresses can be assigned like this. I have 8 ranges of IP address. I have 8 subnets. Each subnet will have 2 to the power 9 hosts.
Do I need to tell my service provider that I'm using 3 bits for subnets?
You don't have to. We will talk about this. These actually affect very much how you design your routing table in the routers. Okay? But for Orido, they don't have to. That's in fact a very good question. This is a very good question, really.
What's the logical separation?
This logical separation is internally, but Orido, they only need to know what any traffic that comes with any IP address in this range, send it to QU. ماشي? QU بقى will have to worry about internal routing inside QU. So this is the logical thinking. Okay? So we can talk about this after the break. But this is the state that we have now. We have 8 subnets. Each subnet will have this number of hosts. ماشي كده؟ So this is how we allocate the IP address into subnets, of course I can perform this subnetting multiple levels again and recursively, which means that I can divide this /20 address space into 8 subnets. Each of these subnets will be /23. Each of these is actually a separate network or a logical isolated network. I can then take this network and perform another level of subnetting. For example, I can make it /25, which means I can subdivide this network into 4 different subnetworks, which will be /25. And I can do this recursively over and over again. Okay? For each of these, there is a router in the middle that separates all these ranges of IP addresses. So this is when it comes to address planning. The second part, but we need to talk about routing. How do we design the routing table based on this address planning? Okay? So imagine if I have a network, let's just use some local examples أفضل. Let's say that this is مثلا أريدو. This is the ISP. أريدو, they have a router here, big router. طبعا there is a topology inside. And here, let's say that this is QU مثلا. And this is the HBQ مثلا. Okay? So this inside QU, there are multiple subnets or sub-organizations. Okay? So each of them is /23. This is the exact same example that we have in the previous slide. So inside QU, I decided to subdivide the range of IP address, which is 200.23.16.0/20, into 8 logical subnets. Each of them will have a separate network part and separate host part. So which means that 16 here, this byte, it looks like this, 0001, 0000. Okay, and then I add طبعا this part belong to the host part, صح? 23 starts at the very last bit. Okay, that's why you can see that from 1 to 1 here, I'm adding 2, because this bit is always 0. So either you add 2 or 4 or 6 or 8 and so on. Okay? So I can have up to 8 organizations that look like this. Okay? So this is the hierarchical addressing. In that case, the QU, if they have a router here, مثلا, they store in the routing table 1 entry for each organization. So if I have a packet that comes to QU, this router needs to distinguish definitely between all these subnets. صح? We have to. Yeah? Which means that the routing table here has to have at least 8 entries. 8 entries, okay? To distinguish between the packet should go here or here or here or here and so on. Assuming that the router has 8 ports or more. ماشي كده؟ So depending on the destination IP address that we have here in the packet, it goes to this router, and the router tries to match this address with one of these organizations. Okay? واضحة كده غلط كده؟ تمام. So this is the how we perform routing. That's the easiest part. So now, if this router بقى اللي هو ISP level router, okay, needs to distinguish between the packet that should go to QU or the packet that should go to a HBQ. Okay? So in fact, I can have more than 8 different entries to say that each of these entries will have to end up here in this router. Or what I could do is that I can have only one route entry here, okay? That this should go to QU, but I don't care whether it goes to organization 1 or 2 or 3. So in that case, here we store only one entry for whole QU, which is 200.23.16.0/20, and this goes to interface 1, for example. Anything in this address range should go to interface 2. This will be a simple routing table with only 2 entries. So this way, I saved a huge amount of routing table space. Okay, so this is also one of the advantages of address planning, is that I can perform what we call a route summarization or route aggregation. I don't have to store a routing entry for every single network in the internet. I can always perform route summarization or route aggregation, okay, based on this address space or address plan. That's one of the reasons that we do this subnetting, is that we can facilitate how to summarize group of subnets into one routing entry. Okay? تمام؟ طيب. So if we have an ISP and if we have this particular example that looks like this, this is what we need to do is that here, this router needs to distinguish between all these organizations. So it needs to have 8 entries in the routing table. There's no escape around this. صح? But this router can perform route summarization. In fact, the way that we do routing, using some routing protocols. Routing protocols, they perform what we call update messages. Routers, they exchange update messages. So what this router will inform all the other routers is that I have 8 different networks, and these are the addresses of these networks. Okay? So when this router receives the addresses for all these 8 different networks, it should perform this route summarization or route aggregation. So it kind of knows that all these ranges of IP address, they can be summarized into one network address /20 instead of /23. ماشي? As long as all of these networks are connected on the same port. So I can do aggregation per port. So all of these networks are connected on the same port. So we can do that route aggregation. But here is a very interesting example. Okay, very interesting example. It's very specific example. If I decide that, let's say, hypothetically, let's say that the address 200.23.18.0/23, this network, I decided for whatever reason to move it to this organization.
You can't do something else.
Why? I can. Why not? I decided to move it to this. We want to see what is the implication on the routing table in this router, and in this router. Okay? First of all, can I do this? The answer is yes. Will this lead to any confusion? The answer is no. Given, ده لا ما انت ما تلخبطناش يعني. برايفت بابليك ده احنا بنتكلم على نات. ما هنا لا هنا ما فيش. هنا actually none of these ranges is actually private خالص. All of these IP addresses are public IP addresses. Okay, it has nothing to do with NAT. Okay, but can I do this? The answer is yes. We can do that. But what is the implication on the routing table, and how can we maintain the consistency in the routing table, okay, And will route summarization work in this scenario? And the answer is also yes. Okay? طيب بس ازاي بقى؟ When this network moves here, definitely this router needs to be updated. So this router will have to have at least two entries. Sorry, we'll have to have this entry اللي هي 200.23.18.0/23 and any other network here, whatever the address is. So this will have to end up here. Okay? طيب, what about this router بقى? Will it be affected by the fact that this organization moved from here to here? Update, صح. بس update ازاي بقى؟ هل بقى يعني will this router say no, based on that summarization cannot work, so I have to break down this address into 7 different addresses and one that belongs to the other router. Or route summarization can still work in this case. Route summarization can still work, and this is good news. But this router needs to have 3 entries in that case. 3 entries in that, and instead of 2, it will have 3. Okay? So let's see بقى what these entries are and how this will eliminate any kind of confusion. That's what we need to do now. Okay? So simply this router will have to have 3 entries. One is the summarized route, which is 23.16.0/20, and this will have port 1. Okay, lower port 1 this. Okay? And we will need to have 199.31 lower this one. Okay? .0.0/16, and this will be in port 2. And the 200.23.18.0/23, and this will be port 2 as well. Okay? So if this router maintains these 3 routes, there will be no confusion. At only how does it distinguish between, because this address is part of this address range, صح? Okay? متفقين, صح? This address range is part of this address. So how come we separate them like this? Okay? And the routing will still be consistent. Okay? That's based on the magic of the maximum match rule that we talked about last time.
Yeah.
Okay? So if we have an IP address that matches 2 rows in the routing table, we select the one with the highest number here. Okay? So based on this rule, there will be no confusion. Okay? So this moving will not affect anything. Let's see. Type. So let's apply this. Let's apply some examples. So this is the routing table now. So we have, again, let me write it again. 200.23.16.0/20. And this is port 1. And 199.31.0.0/16. And this is فين دي كانت معرفش ما علينا. Okay, and 200.23.18.0/23, and this is also a port 2. Okay, طيب. Now I'm receiving a packet at this router. I'm receiving a packet with a destination. This is the destination IP address. And this destination IP address is as follows. 200.23.17.4. This is a complete IP address, Okay? Which port does this go to?
The first one.
This is ايه؟ طبعا خد بالك. Here, remember, I don't store any subnet mask in the IP address. In the packet, I don't store this. Okay? So the question now is that from this destination address, which port does it go to? What the router will try to do now is that it will try to match this with the routing entry. Okay? Of course, it does that in hardware, and it's very fast. Okay? But for us, unfortunately, we have to do it manually or visually. So this one, if we separate this 20 bits, we see that the first 20 bits here clearly matches this. صح؟ حد مش عارف ليه؟ The first 20 bits here clearly matches this address. Okay? حد مش عارف ليه؟
Because byte and half of that.
Right, so this 20 is again at the third byte. So we need to convert this to binary. 16 is 0001 0000. And 20 here is like this. The first 20. So the first 20, 8 plus 4, صح? So these 4 bits, if we separate بقى and put zeros, هيصبح دي 16 and the 17 will become 16. Because the 17 is this 17 is 0001 0001. So we mask this part. We mask this, we put it 0. It becomes 16. The 17 becomes 16. So we have a match here. Okay? So that's a good match. So we have a match now. That's good. Okay. Does it match here? In order to match here, we have to take the first 23 bits, which means these other 3 bits will be included. And it has to match 18. Okay, it has to match the number 18. Number 18 is what? Is actually 0001 0010. This is 18. Okay? 23 معناها هنا. Okay? So when you mask the 23 bits, it becomes also 18. But this is 17, so there is no match. So this means that we have only one match. We have only one match, which is this one, and this means that you have only one port to go to, plus. That's fine. Okay? Right. If we have something like this destination address is actually 200.23.19.100. Okay? Does it match the first one? If we do the same exercise, yes, it matches. صح? Does it match this third row? It does match. صح? طيب, so we have 2 matches now. Which one do we select?
Maximum.
The one with the maximum subnet mask. So we select the one with the 23 because it's larger than 20, which means that we select the one with more exact match. Yeah, this is the idea. We select the one with more exact match. Okay? So this way we have no confusion given the rule of match based on the maximum subnet mask. So we can perform this movement and not affect route summarization. We still maintain the small size in the routing table of the ISP. Okay? The route summarization is still maintained. ماشي? We saved a lot of size in terms of routing table. So the benefits is still maintained. ماشي كده؟ خلينا نشوف. اوكي. في أي حاجة مش واضحة في النقطة دي؟ We shouldn't spend all this time actually في الجزء بتاع subnetting, but that's fine. Now we need to talk about ICMP. the control management protocol. As we talked about, the protocol suite for the network layer includes a IP version 4, ICMP, okay, and other protocols. They form what we call the protocol suite, the IP protocol suite. So ICMP is one of the protocols in the network layer that works hand in hand with IP. For what? For troubleshooting. Okay? We use it for troubleshooting. For example, if we need to know that there is a network, مثلا in China, we need to know whether this network is actually reachable. مجرد reachable بس. أو there is a host and we need to know whether it's reachable or not. Like for example, I need to know whether the Google website is actually running ولا لا. Okay? So if I have the IP address of the Google server, I can simply use ICMP and say ping that server using the IP address. If I get some reply, this means that the server is running. Okay? If I get no reply, this means that this server is not running. Okay? That's one use for ICMP. The other use is if I want to know better, not only whether the server is running or not, how do I reach there? What is the probable path to go from here all the way to Google server? Okay? What is the probable path? What do I say probable path?
Because it's dynamic.
لأن it's dynamic. لأن يعني if I send multiple packets to the same destination, they don't necessarily have to take the same route. Each time they might take a different route because IP is best effort. IP never provides any guarantees. That's the whole idea of trying to keep the core network simple. تمام? So these are basically the functions for ICMP. ماشي? So ICMP provides يعني simply two messages: echo request and echo reply. This echo request and echo reply. Very, very simple. IP version 4 defines, ICMP version 4 provides two simple control messages: echo request and echo reply. So ping definitely uses echo request message. It tries to send ping. It tries to send an echo request message and provide the IP address. If that IP address responds with something, which means the ICMP protocol running on the final destination responds back with an echo reply. Okay? Then this means that this server is up and running and everything is fine. So I know that I can reach that server. Or if it doesn't, then I get back some of these error messages. Okay? So if it does not respond as I expect, then the network itself will give me one error message from this. Whether this network is unreachable, or this host is unreachable, or the port is unreachable. This port is unreachable is an interesting thing. This means what? Port refers to the application. This means that the host itself is there, but the application that is supposed to reply, the application itself is not running on the host. Okay?
Could it be a service that is down?
Service is down. So this means that the host itself is there, but a service running on the host is not running.
It's not running.
Yes. Okay? So these are the error messages that we get. Or if we get zero code and zero type, this means that everything is fine, the server is running, and life is good.
So when the IP is assigned to a host, for example, and at a moment of time it is disconnected, or I
Right.
close, how does this instance go to another host, or does it the host, the IP, it's directly assigned to a different host?
لا ال IP is assigned dynamically to hosts based on their location. يعني if you move your laptop مثلا from your house to QU, you get a different IP address.
Okay,
صح.
the previous one is assigned to different host.
it may be assigned to different hosts, or it may not be assigned to anyone.
So, for
Okay.
example, if I come back to my house and
Right.
do the same application, it will have different hosts.
Yes, it will have different IP address. Yes.
I thought it
IP address is location based. IP address is location based. That's why we actually use the IP address to identify the location of the person.
If I open the same exact page, it will not be assigned the whole.
Yes. Yeah, that's why حتى if you have an email and you're trying to identify where this email came from, you get the metadata of the email and then you get the IP address, right? And then you look up where this IP address, it gives you the location.
Doctor, in a corporate network with servers, I try to fix the IP for that specific server.
صح. This is what we call اللي هو DHCP, dynamic address allocation. That's another story, but يعني you can designate in the network that some hosts will have fixed IP address. If this host is connected on the network, it will always be assigned this IP address. If it's not connected, this means that this IP address will never be used by any other host. So these types of hosts, we usually use them as servers. Okay.
When you track back an IP address, it leads you only to the router. That's the maximum you can reach, is it?
يعني لا يعني when you track an IP address, which means ping,
Yes.
it gives you the final whether the final destination is running or not, but it doesn't give you anything about the route.
Yes.
Okay, so there is another message بقى, or there is another part of the protocol that gives you that route. So ICMP itself as a protocol defines echo request and echo reply and all the possible error messages associated to them. Okay, but there is a small trick here. If we use it for ping, it's easy. Echo request, if we get echo reply, everything is fine. Right. What about trace route? For trace route, what I need to know is I need to track that the packet goes from this router, and then this router, and then this router, and then this router, all the way to the final destination.
How many routers?
How many routers does the message go through? What is the IP address of each of these routers? Okay? From here all the way to China, مثلا, ولا to any place. Okay? That's another command in ICMP. It's called by a trace route. So trace route still uses echo request and reply. Okay? But there is a small trick. In order for me to kind of trace the routers along this path, there is a small trick that I have to do with the message. Okay? What I do is that, خد بالك, one thing we should notice here, ICMP messages are sent with an IP header. Okay? يعني for IP, ICMP is like TCP and UDP, anything that on top of IP. So with the ICMP payload, which represents this echo request and echo reply, I need to add an IP header. So this IP header contains all the fields that we talked about, a destination IP address and TTL. TTL is a time to live, right? Which is, as we said, it's misleading and it should refer to number of hops. So that's the trick back. In traceroute, what I would do is that I will send first a ping message to the final destination, but with the TTL equals to 1. Okay? So from the host here, I will send a message with TTL equals to 1. This means what? This means that it will come here, this TTL will be decremented to 0. Okay? What will happen in that case? خلاص, I cannot send it further, but what I will do is that I will send back this echo reply with this error message. TTL expired. Okay? And who will send this? This router. So this router will put the IP inside the ICMP payload, okay? And it will send it back. So this gives me which router sent back this reply, Okay? And from the error message, I get that the IP of the first router. So if I need to know the second router, I will send another echo request with TTL equals to 2. So this means that this router will reply. And I will keep incrementing this until I receive this one of these messages بقى. Whether it reaches to the final destination, I get anything other than TTL expired. So this means that it reaches the final destination. Or I have to stop خلاص لأني خلاص I don't have to send any further. Maybe the network itself is unreachable. Okay? But I will try to get you through all the way to this network. But maybe the network is unreachable, so I will stop at a certain router خلاص. The router will not echo reply and say TTL expired. It will say something else. Maybe this network is unreachable or port unreachable or reachable, whatever. So if I get anything other than TTL expired, then I stop. And you get all the entries from the first router throughout all the routers. If it stops and it doesn't give you the final IP address of the destination, then you know that this final destination is also it's unreachable. Why? Because this router stops it. Yeah, so this particular router stops your traffic from going to the final destination. Okay? يعني this particular ISP router هو بقى السبب هو ده السبب يعني.
So Victor, if I track back an email, I will track it to the local network, and that's the maximum I can get.
لا هو انت if you want to track an email, you open the metadata of that email, then you get the IP address where this email came from.
Yes.
First you can ping it to see whether this is running or not. You can trace route. If you trace route, it gives you exactly how to go there. But usually for the email, you want to know the location, where it came from.
Yes.
So in that case, you can look it up, or you can do trace route, but trace route will give you IP addresses and delay information, but it doesn't give you, مثلا that this router in China, this router in Kaza, this doesn't give you.
So I thought there is a website.
There's a website, yes, you can look it up. Yes, you can look it up. You can look it up.
Doctor, at the corporate level, do we do?
Yeah, we use the trace route very often for troubleshooting. Definitely, very often.
Do you go back
Yeah, sometimes you discover some inconsistency in the routing table of some routers because of this. As I said, I mean, if you do trace route and then everything goes well until this router and then no further traffic, then you know that there is a problem in the routing table of this router.
But as an SME, will I go and try TTL1 and then I'll try
No, you don't do this. If you do trace route, it will do this internally.
do this
Internally,
So I
incrementally.
have to write it.
Yes, you just have to write the command trace route and then you give it the IP address. Then it gives you the first router, second router, third router. Okay? Once it stops, if it stops at the final destination, then you know that everything is fine and the final destination is reachable. If it stops at certain point, but it does not include the destination IP address, then you know that this particular router does not or stops the traffic from going any further. That's a way to troubleshoot how the traffic goes all the way to the final
I
destination.
want to just mention something that we did use it for this one, like at corporate level. We have a cloud agreement with one vendor.
Right.
Yeah. So our customers are complaining
Right.
about the slow response. of
Right,
this
right,
application.
right.
So what we have done is that we were trace routing,
Yes.
and then we found out that our traffic was going back to Canada.
Yes. Yeah, see? Exactly.
And then we proposed,
Yes.
how about you use something
MashaAllah, you
in
have
Whiteboard?
hands-on experience. Yes. Which doesn't make sense, huh?
But it does
It
not
doesn't.
make
It
sense.
doesn't make any sense.
Why my customers need to wait for
Yes.
they're from Qatar.
Yes. So you can pull the phone and call Uridu. You need to fix this issue.
It's not actually Ooredoo, it's the cloud service provider. It was Oracle.
Could be. Mish.
Oracle are bad.
Mish. But in that case, you just have to
That's Oracle cloud
update the service provider, whoever that service provider is, to fix that problem. And what they need to do is that maybe they need to fix their DNS, or maybe they fix the router to have a route entry manual. They do this sometimes manually. Yes. To just put a route in the routing table of the router to just allow your traffic to go directly.
So this can be also resolved from the service provider?
Yes,
So
it could be.
from the cloud service provider?
No. Cloud service provider usually they do not have routers. They have VMs.
No,
They have data centers.
Yeah, that data
VMs, yes. So they can make sure that the VM that has this particular IP address is up and running, مثلا. Or if they have a cloud, sometimes they have like a distributed cloud. Okay? If they have distributed cloud, your traffic is supposed to go to the cloud مثلا in Qatar. But for some reason it goes to the cloud service in Canada. Okay? So again, you tell the service provider, why do you allow my traffic to go to Canada instead of being accessed in Qatar? Then they need to do some adjustment in the VMs, and off you go. Then your traffic will go to the particular VM. They fix that sometimes through gateways.
But Doctor, that's specific because it's a cloud service.
Yes.
That means there is a specific server, yes?
Specific server, but there is, for cloud service providers, they have what they call gateways. These gateways, they kind of dispatch the service requests to the different servers all over the world. They have a gateway which usually, it exists somewhere. Okay? This gateway takes the traffic, and then based on some agreements, it say send this to Canada, send this to China, send this to. This is different from the internet service provider. This happens at a gateway level, at a higher level. But again, it has similar rules.
So the solution can be.
In all cases, it can be tracked using the trace route. Yes.
Okay, good.
So you can fix this through the service provider. Then they have to update their gateways. Or it can be fixed through the internet service provider, URIDU, by fixing the routing table. But in all cases, it can be done. طيب. عشان احنا we spend a lot of time. This is the trace route, and this is the. So that's what's explained here. So the first message I will send a repeated. طبعا احنا for ICMP it's sent from the transport layer as UDP segment, which will have an IP header and will have an ICMP payload. Okay, so each echo request will be sent as UDP message encapsulated inside an IP header, and will have a payload of ICMP which will contain the echo request and echo reply. So it's like a control message. It doesn't have any data. There's no data in it. That's why it's called the Internet Control Management Protocol, ICMP. So it's not used for sending data back and forth. It's used for sending control messages only. Okay? So if we get this TTL expired, then we know that this is the router that sent it, and I keep doing this until I reach to some error message or some echo reply that it has reached the end, then I stop. Okay? So this is the idea. Type. Do we have time? I was supposed to go through this. Let me just introduce this topic, and then we can continue next time. I was supposed to finish it today, but because of long discussions. Type. This is about the second school of thought. And we talked about CIDR and IP version 4. Until now, we are holding our hands to IP version 4, saying that, okay, it can still survive. طبعا, how? By introducing CIDR, introducing this subnet mask, okay? But we did do something else that we discussed in Network 1. What you mentioned that, اللي هو الايه؟ NAT. We also invented the concept of network address translation. Network address translation, I will talk about it conceptually. You don't have to know the details. But network address translation is one of the approaches that we have introduced in IP version 4 to again keep it alive for a longer period of time. How? So the idea is simple. So we are saying that we have IP address exhaustion. Even with CIDR and we have arbitrary subnet mask, we still have this IP address exhaustion. Okay? So one idea came out that, okay, so we can have range or ranges of IP address that we can use all over the world. يعني معنى إيه؟ This IP address is supposed to be unique for a particular host. Okay? So if I have a host in China with an IP address 200.13.1.1, I should not have an IP address in Qatar with the same IP address. So IP address is supposed to be unique worldwide. Because as we said, it kind of indicates your location. Okay? NAT violates this assumption. It says, I have an address range which can be reused. Okay? So if you look at your home router, for example, you see that your home router always starts with 192.168.1. صح? All of us, we have the same thing. Okay? So if you try to look up and say, I need to know the location of one, this is a very naive question. It will give you no answer, of course, because it's used all over the place. Okay? But that violates the uniqueness of IP address. That's why they came with another protocol called NAT. It's beautiful in the sense that Ooredoo doesn't have to give me number of IP addresses equals to the number of devices that I have at home. They don't have to know how many devices you have at home. Okay? How many addresses do we get from Ooredoo as users? One. We get only one address. So how come do we have tens of devices in our houses using the concept of NAT? Using a concept of NAT, we use a range of IP address. We call it a private IP address. So the private IP address has significance only locally. All of us can use this private IP address. But when our traffic goes out to the internet, it has to use a public IP address, which is the single IP address that Ooredoo gave us. So as long as we are inside our house, the IP packets, they can play around, okay, using the private IPs. I can send from one device to another. We can play around games and stuff like that, and we use the private IPs, okay? If I want to send anything outside our house, the router will have to map the private IP to a public IP, and it's only one IP. So it goes out. لا هو لا اسمه public IP.
But it represents the router.
The router in that case uses NAT. It's not gateway. Gateway is application layer, is higher layer. But the router in that case uses the protocol NAT. Okay? Again, using this simple approach, I don't have to give each one tens of IPs. I can give you only one IP, and that's enough. Okay? Even QU, logically, they can use private IPs inside QU, which means technically Ooredoo can give QU only one IP. But the problem is this private IP cannot be used on servers. Because again,
I need to fix the IP.
yes. And this IP should be exposed to people who are trying to use it.
Yeah.
This is the problem now. Okay? So I cannot give QU only one IP, and QU can say, okay, so I can have tens of servers and people can access it from anywhere. That's not easy. Okay? It will make the service very disrupted. So the private IP has significance locally, and we can use it inside our houses. But once we have a traffic that goes out, we have to use public IPs. Anyways, with this concept of private IP and public IP and NAT, we were able to maintain the life of IP version 4 for a number of years. So first, we introduced the CIDR, and second, we introduced NAT. So these two concepts have preserved the life of IP for these number of years, despite the fact that we definitely have more than 4 billion devices in the world, right? طيب. The other school بقى said, okay, so forget about all of this. We want to do something drastic. وسع. Let's do it revolutionary. Okay? So what is this IP address exhaustion? Let's just use 128 bits of address and forget about all of this. Okay? Easier said than done. So we will see the implication of this. Of course, we can learn lots of things from IP version 4. We have learned so many lessons. We know that so many fields in IP version 4 header are actually not being used, at least usefully. Okay? So we can design IP version 6 with these lessons learned. But also we have to enlarge the address space يعني drastically. Okay? So we have increased the the IP address size from 32 to 128 عشان بقى ايه يعني خلاص بقى we don't have to say 32 وبعدين 34 لا خلاص بقى let's just solve it once and for all. Okay?
You said only 1% of the device in the whole world.
Yeah, but this is one of the main problems of IP version 6. So one problem that they have thought about is that, okay, so IP address version 6, we can learn a lot from IP address version. We can design it very nicely, okay? But how can we deploy it in the internet? Can we just say, no, in order to allow all the routers to use IP version 6, let's just shut down the internet for a number of days, okay? Until all the routers are updated to IP address version 6 and then we restart. Can we do this? Of course we cannot do this, okay? Because IP is based on decentralized architecture, okay? So with decentralized systems, always comes a challenge that when we deploy something, we have to do it gradually. We have to have gradual deployment, okay? So what we want to study in this part is that, okay, how can we design IP version 6 header based on these lessons learned? What fields have been introduced newly or added in IP version 6, if any? What fields have been removed and why? Okay, what fields have changed? Okay, and why? And so on. Okay. The other thing is, how can we perform IP address version 6 gradual deployment? That's very important. How can we allow the internet to build IP address version 6 and still maintain some interoperability? يعني بمعنى آخر, currently nowadays, I need to have networks which use IP version 6 to talk to another network that uses IP version 4.
Yes.
But this violates the protocol stack definition, right? Because in order to understand each other, we have to talk the same protocol. How can we allow a network that uses IP address version 4 to talk to another network that uses IP address version 6? We cannot. Logically, we cannot.
Those 1% devices are only communicating to each other.
لا طبعا لا, they talk to other networks with IP address version 4, but there is a trick. There is ايه؟
Do they encapsulate what?
Yeah, برافو عليك, أنا عجبني طريقة تفكيرك صحيح. We have some extra encapsulation that has to happen. Okay, we call it tunneling. So tunneling talks about extra encapsulation that has to be done in order to encapsulate an IP version 6 payload inside an IP version 4 packet, or the other way around. So by doing this encapsulation and decapsulation, we can allow the networks to talk to each other even though this is version 6 and this is version 4. But how this tunneling is designed, okay, how can it maintain the layer stack? That's what we need to answer next lecture, inshallah. Okay.